Okay, now we are live. Hello, everyone. Welcome to the 3D TV seminar series. Today it's our great honor to have Richard Hao Zhang from Simon Fraser University. So Richard is a distinguished professor at SFU. So he works in. Welcome to the 3D TV. He works in the broad area of in the area of shape analysis, geometry processing, and recently in 3D vision. So he has won many awards, most notably including the CVPR Best Student Paper Award last year. And he's let's welcome Richard.
Thank you, Qixing. I hear some echo. Is that a problem for the audience? I'm not sure. So that's the way it's going to go, right? Because there's a bit of a delay. Okay, then I will go ahead then. Thank you, everyone, for come to the seminar. So my talk is about 3D shape understanding, but my goal here is more than just recognizing or classifying the objects. It's beyond what it is. Like in here, you see that there's a room, and then you know, you have an algorithm that may be able to recognize there's a TV and there's a bookcase and things like that. What I'm interested in is actually seeking the right shape representation. So first of all, if you have the right shape representation, it could facilitate the recognition or classification tasks. But more importantly, I really like us to be able to manipulate or interact with the 3D objects. And of course, it will be also nice to generate 3D objects. And these all call for the right shape representation. So then the natural question is, what is a good shape representation? There's got to be multiple answers. So in my talk, I'm going to focus on two criteria that I think are fundamental and also well practiced. So the first one is what is generally known as the Occam's razor. So it essentially says that all factors being equal, the simplest, or I would use the term compact, the most compact model or explanation tends to be the best one. And there's another term that is being used, which is called the minimum description length principle, such as another term for the Occam's razor. So in machine learning, I guess the prototypical example of something that follows such a principle would be the autoencoders, right? So when you have this bottleneck layer, by restricting the length of your latent code, you are essentially forcing the network to learn the essential features of your training data. Now, because we're looking at shape understanding, shape perception, and you like the algorithm or the machine to be able to do what humans would do, then we certainly like to have a representation that mimics the human perception. So this is a paper, a very classical paper, not from computer science, it's from cognition from the 1980s. Many graphics papers, I think also vision papers cite this classical paper. And I'm going to take a quote from the paper. It says that for object recognition, the human visual system decomposes the shapes into parts, and the parts with the descriptions and the relations between the parts form at first index into a memory of shapes. So this paper is all about the importance of structures. So structures refers to the parts, their properties, and also their special relations. So with this in mind, we certainly would like to have a structural representation for 3D shapes. So let me just sort of get right into it. So I would like to introduce, if you haven't seen this one before, a representation which epitomizes both of the criterion that I mentioned. One is the simplicity or compactness, and the other one is structural. So this representation for 3D shapes is called symmetry hierarchy, and it uses a symmetry to guide the grouping and assembly of shape parts, and it's a hierarchical representation. So this was work done quite a number of years ago. Now, as you can see, I'm using symmetry as a driving force behind this representation. So why is symmetry important? Well, there's some obvious reasons. So symmetry grouping, the fact that humans tend to group entities based on their symmetry is one of the Gestalt laws. And there, of course, there are some other laws that people use often in perception. And another important property of symmetry is that symmetry reveals redundancy, right? When you have reflectional symmetry involving two elements and you have rotational symmetries of various orders, they essentially say they are the same thing, right? So it introduces this redundancy. Now then you can do something with it. If you are able to remove the redundancy, then you can achieve certain efficiency. So an example of that is actually not in visual computing or anything, but in solving constraint satisfaction problems. Then if you can find all the symmetries, then you can reduce the search space for the constraint satisfaction problem. And back to visual computing, everyone saw this picture, right? This is the classical picture from the Martin Cubes paper. And we knew that by looking at all the possible signs at the corners, you should have 256 cases. But by identifying symmetry, you can reduce the number of cases to 15 or more. Well, this is actually the original picture, and it's actually missing a few cases. And generally speaking, if you're able to identify the symmetries and the redundancies that are from that symmetries, and you remove them, you can lead to efficient and compact representation. So now let me define symmetry hierarchy for you. So we have a 3D shape. We assume that it has a part segmentation, and then we identify self-symmetries of each part, and also the symmetries between the parts. So in particular, there's the rotational symmetry, and here the red edges identify rotational symmetry. And there's also reflectional symmetry given by the green edges, and also connectivity, which is given by the blue edges. I do have my pen tool here enabled, right? So these set of edges form an initial graph where the nodes are the parts and the edges tell you the relations in terms of symmetry and connectivity. And then you can perform grouping, right? So you can group by symmetry. So here are two arm rests that are symmetric to each other. Then you can group them, and that leads to a graph contraction operation. You can also perform grouping by which is called assembly. So as long as two parts are connected, you can group them into the same node. So there are two kinds of operations, and you can perform these sets of operations bottom up, and then you're going to form a hierarchy. So the interesting question here, of course, is what would be the best order with which you should be grouping these nodes, right? So how do you perform these graph contractions? There's something which is optimal, the most meaningful one. So the first attempt, which was done 10 years ago, involves no deep learning or anything like that. It was just a model or rule-driven approach. Essentially, we thought about the principles that we should follow. So symmetry grouping would be one, and the other one is the compactness principle. And simply stated, we try to have as few operations as possible. We try to make the hierarchy as small as possible. So with those things in mind, we came up, I think, a total of 7 handcrafted precedence rules. I won't be able to go through all of them, but I'll show you 2 examples just to give you an idea how these principles are being adhered to. So here's an example of a few parts. You have A1, you have A2, and you have B, right? So there are a few things you can do here in terms of grouping. You can group A2 and B first. This will be a grouping by proximity. Or you can group A1 and A2 first. It will be a grouping by symmetry, right? So we had one rule which is called M1, and then this rule says that symmetry grouping takes precedence over assembly. Okay, so because A1 and A2 are symmetric, you should group A1 and A2 first, and then you group that together with B. So that's one principle. However, there's an exception. In such a case where you have A1 and A2 being symmetric and B1 and B2 being symmetric, right? So the rule M2 says assembly before grouping. To refer to, in this particular case, you should first assemble A1 and B1 and then model a reflection symmetry. Why do we do that? Why is that better than grouping this and then do assembly? That's because assembly before grouping here results in 2 operations. And if you do this in the other way, you get 3 operations. So this is an example of the compactness principle at play. We'd prefer to have fewer operations. This is why we have the rule M2. And another example would be, in this case, you have a rotational symmetry, which is of order 4, and you also have a reflectional symmetry between A1 and B. Then the rule G1 says that rotational symmetry takes precedence over the reflection symmetry. Again, this is so that we're able to have fewer operations in the hierarchy. Okay. Now, here are a few things that are nice about the symmetry hierarchy. So first of all, it's structural. So it mimics a human visual perception as per the 1984 paper. And because it identifies symmetry and groups objects based on their symmetry, it removes redundancy, which results in a more compact hierarchical representation. And finally, we note that this representation decouples structure and the fine-grained part geometry. Right? The hierarchy itself doesn't really care about what the individual, mesh triangles are and their fine-grained geometry. It only cares about whether 2 parts are connected and whether the parts are symmetric or not. Right? So the part symmetry and part connectivity are encoded by the hierarchy, but part geometry, they can be encoded within each leaf of the hierarchy. And then we'll see later that this kind of decoupling is a nice property for us to be able to have a nice generative model for 3D shapes. How do we learn symmetry hierarchies? Can we come up with a learning method to construct meaningful hierarchies? And then would it be possible to use that model to eventually lead to a generative model of shape structure? So that's what I'm going to talk about next. So thinking about trying to develop a neural network that can learn symmetry hierarchies, what I guess first would come to mind would be the traditional CNN, but it turns out that there is a better fit. So CNNs are not exactly a good fit for modeling something like a tree structure. Fortunately, there are these so-called recursive neural networks, which had been developed since the 1990s, but somehow they're not as well known as the other network architectures. So recursive neural networks really turned out to be a perfect fit for modeling and learning symmetry hierarchies. So what is an RVNN here then? So RVNN stands for recursive neural networks. So it's a tree structure. It's a tree of networks where each node is the same neural network. So all the nodes share the weights for the network. So one node can take on 2 vectored inputs, and then it's going to produce another vector, say, of the same length, and you have another node, and their outputs can be recursively fed into, again, the same neural network to produce an output. So this is the basic structure of a recursive neural network. So we're going to use RVNNs to learn symmetry hierarchy. So here, a shape like a chair here, I'm using a 2D example, is abstracted by using an arrangement of boxes. Again, at this level, we don't care about the individual part geometry, we just care about the part relations and their connectivity. So each part is abstracted by just using a cuboid. It's a box. And these boxes would have their encoding using a network. And these encoded boxes would be the leaves of the RVNN, the recursive neural network. Now we need some kind of a network loss, okay, to define what would be a good order to perform this recursive combination of the nodes. So this was the first innovation. So beyond the previous known works on recursive neural networks. So we turned the RVNNs into a recursive autoencoder, right? So the encoder is going to take a set of boxes, a box arrangement, and it's going to recursively combine things. It's going to come up to a root code, which is the one you see here in the middle. And then the decoder is going to take a root node and recursively decompose it into a set of boxes, right? And now this is, you get an autoencoder, a recursive autoencoder, and the network loss is just a reconstruction loss summed over the boxes. The network here is trained to try to reconstruct the box arrangement. Now, to turn this into a generative model, we note that if you're able to have a way to produce plausible codes, let's say for a particular shape category, then you will be able to then sample a code from that learned model and then produce a shape structure, right? So this essentially was the idea. So then we turn the autoencoder loss into a GAN loss. In fact, it's a variational autoencoder to learn a manifold of plausible codes. And this network is trained over a particular shape category like chairs, as you see over here. And that allows us to be able to sample from that learned manifold and to be able to produce novel shape structures for a particular shape category, such as chairs. And then finally, using a separate neural network, we're able to fill in the part geometry. And finally, you're able to obtain an actual shape, right? So that part geometry is modeled using voxel grid. So overall, the generative process is to sample a root code and then using the decoder of the network to produce a symmetry hierarchy, and then use a separate neural network that was trained to fill in the part geometry. And the key here is that we're decoupling the generation of shape structures, which are this arrangement of boxes forming a symmetry hierarchy, and the generation of shape geometry. And the result is that you get cleaner parts, right? So first of all, of course, you get structured output, unlike previous works at the time. And you get parts, okay? You also get symmetry relations between the parts, right? And because you're able to separate the shape into parts, for each part, you're able to get, say, a particular resolution, and overall, you get a higher resolution for the shape, and the outcome are much cleaner compared to if you were to develop a generative model for the whole shape. And also this network, which we called GRASS, or generative recursive autoencoders for shape structures, was also the first RVNN that can learn multi-attribute graphs. Okay, do note that for the symmetry hierarchy, not all nodes are the same, right? There are nodes that model assembly, and there are nodes that model symmetry, including both rotational, reflectional, and translational symmetries. So since then, this work that we call GRASS had been followed up by some other works, all are in the similar spirit. And what we did was actually to generalize the RVNN for 3D shapes to 3D scenes, which was kind of a natural extension. Then the shape parts are the objects in the scene. And all the scenes you see here on the slide were generated using a random vector, and was actually pretty fast. It was a fairly effective data augmentation method for indoor scenes. Now, going back to one of the questions that we had before, which was whether we're able to learn the handcrafted rules, which there were 7 of them from 10 years ago, without telling the network what are good symmetry hierarchies. Okay, remember the notion of what is a good symmetry hierarchy was essentially handcrafted, and with that, we came up with 7 rules. Now, after we train this GRASS, this neural network, we do not use any ground truth symmetry hierarchies to train the network. However, after training, we try to test whether the network can recover the 7 rules right, which were handcrafted. For example, grouping, taking symmetry grouping, taking precedence over assembly. So this is M1 here. This is the example that you saw. And there's an exception to that, which is assembly before grouping if you have this situation. And then there was also the fact that rotational symmetry should take precedence over reflectional symmetry. We tested whether these rules are recovered by the network, again, which was trained without knowing what are the ground truth symmetry hierarchies. It turned out that almost all the rules, the 7 rules, were recovered by the neural network. And except for one of them, which is a precedence relation between transitional symmetry and reflectional symmetry. So maybe that really wasn't so natural. Okay. So here, I guess the understanding seems like the network understood something because it was able to recover most of these handcrafted rules by humans. So we would probably attribute that to the compactness of the root code. So in that, we set the length of the root code to only 80. And so these 80 numbers are supposed to be able to model all kinds of structures with varying depth of the hierarchy. Right? So perhaps that compactness forced the network to learn smaller hierarchies, hence adhering to the handcrafted rules that were developed before. So the graph still had a lot of limitations. So one of them being that even though it didn't take ground truth symmetry hierarchies, but it did require ground truth part segmentations. And also, it only cared about whether 2 parts are connected for the assembly. So if they are connected, you can assemble them. But it overlooked different assembly operations. If you think of constructed solid geometry, there are different kinds of assembly operations. It could be a union, could be an intersection, could be a difference. And also, the hierarchy are pretty coarse, right? The structural inference essentially stopped at very coarse box level. If you look at this model here, there's a lot of structures here, right? The different parts, but they are all sort of fit into a pretty coarse box. So the structural inference didn't go down to the primitive level, which may be desirable for certain applications. And finally, the entire work was focused on shape structures, not geometries. And the geometries were represented using voxel grids, which at the time was the representation of choice for 3D shapes. But now we know that neural implicit representations have become very popular since, I guess, CVPR 2019, that because of the continuity of the representation that is able to learn. So there has been a lot of follow-up on these neural implicit representations, and they are indeed shown to be more advantageous for shape representation, learning shape representation compared to voxel grids. So here I'm just listing many of the follow-ups to the implicit representation. So I'm not going to talk about neural implicits because I believe there are at least 3 previous 3DGB seminars on implicits. Andreas and Yaron and also Su and all talked about neural implicits. So I'm gonna just talk sort of one path of like series of works following our initial work from CVPR 2019 called INet. I'm trying to ask the question, can INet learn shape parts? And then following that, there are some interesting development. So this is just a very quick recall on what INet does. So it learns mapping from a 3D point to an occupancy value, which is the inside-outside status of that point with respect to a 3D shape, which is encoded using a CNN. And this is trained on point occupancy value pairs with a very simple MNC reconstruction loss using just MLPs. So the question we had after INet was, can INet be used to learn shape parts? Okay, so this is the original INet with the simple reconstruction loss. So it turned out that the idea was pretty simple. All it took was just to add a branching layer. So instead of directly going from these MLPs to get to an occupancy, we add a third layer, L3 here, which is a branching layer. Okay, so that was pretty much the only change to the original INet. So the purpose of the branching layer is actually to learn the shape parts, right? But the whole thing, the training does not require any part labels as supervision. We use exactly the same reconstruction laws as the original INet, right? So before you get into the final occupancy, you have a branching layer, and each branch is supposed to learn one part for your shape collection. And by the way, each one of them is a single neuron, and then use the max pooling to get the final occupancy, right? So with a proper design of the network, it is able to learn parts. And if there's enough parts that are already learned for the shape collection, the other branches can just be empty. Okay. Another thing to note is that the network is able to allow parts to overlap. So this is done through the max pooling, as you can see. So this part for the airplane and this part of the airplane, they actually overlap. So this was work from ICCV 2019. So with this branch layer added, we have what was called a BAE-net branch autoencoder. It is unsupervised. You're able to obtain a co-segmentation of a set of shapes. The way we train this network is we just take these unlabeled shapes and we repeatedly train that using the network. And then there's only the reconstruction loss. There's no part labels. However, there's a variation of the BAE net as well to support one-shot learning. So you could just take one shape that has part labels, and then you can train the network with both the unsupervised reconstruction loss with an extra label reconstruction loss. Then you can perform one-shot learning. Here, the results you see is the result of one-shot learning with only one shape having part labels. Now, why does this work? So this is where I believe the role of compactness or simplicity comes in. As you note, the BAE net actually has less number of layers compared to the original INet. It has only 3 layers, L1, L2, and L3. Okay, so we have a shallow network, and also we have fewer neurons. Depending on whether it's an unsupervised setting or it's a one-shot learning, we have a different number of neurons, and this number of neurons is relatively small. So because of this compactness or small network, the network is forced to learn consistent representations. Okay, with this kind of a toy example, we have these images with just 3 patterns, right? And then the network is able to learn these simple representations for the 3 kinds of shapes: a diamond, a cross, and a triangle. And to look a bit closer, so we examined the neural axis vision maps. We try to see what each layer actually learned. So it turns out that the first layer, it's not a big surprise really. The first layer learns these linear gradient fields. Okay. In the second layer, these fields are being combined to form simple shapes. And then these shapes are combined again in layer 3 to form more complex shapes. Okay. So it does look like with these compact INet, we're able to interpret what each layer actually learned. Right? Now, the next idea was actually, again, a simple one. We simply try to make this interpretability explicit. Okay, so we saw that the first layer learned these linear gradient fields. Why don't we just make them planes explicitly? So we force the first layer to learn weights that provide planes. Okay, and the layer number 2 is going to combine these planes, really half spaces, and to come up with convex shapes, convexes. Okay, and then finally in layer 3, we're going to merge the convexes into more complex shapes, which could be concave shapes. So again, 3 layers, very much like BAE, except that we explicitly force the network to model planes, convexes, and then unions of them. So that work was the BSP net. So BSP net really came from INet and then BAE net, and then BSP essentially made the interpretability of BAE explicit. So BSP net, where BSP stands for binary space partitioning, essentially they're done by the planes to divide the space into half spaces, and we combine half spaces into convexes. BSP net had the same input as INet and the same reconstruction loss. And the main difference being, 3 layers, and then we force the first layer to explicitly model the planes, right? Each plane takes 4 parameters. They are the network weights, right? And then we have these binary matrices which force the neuron selection to form the convexes, and finally we combine the convexes by performing union and to come up with more complex shapes. The number of planes we used for the experiment was 4,096, right? So in retrospect, what the network did was it takes a shape collection and it tried to best reconstruct a set of training shapes using 4,096 planes. And at inference, we're going to take an input and try to choose the planes and convexes that would form that input shape. The output mesh, because we have the explicit planes, it did not require marching cubes, which was typical for implicit fields that are learned by most of the other networks. Because we have the planes, we can just perform plane intersections to output meshes directly. Importantly, there are much fewer planes compared to the number of triangles from a marching cubes. And we can also get sharp features, as you can see from this illustration, comparing auto encoding using INet versus using BSP net. And because we use the same planes to reconstruct all of these shapes, if the planes are coming from the same neuron, they are naturally corresponding. Right? So the planes can if you somehow find one semantic grouping, by the way, semantic grouping was not learned by the BSP net. BSP net only allows the planes to be matched, to be corresponded. But if you perform a semantic grouping of one set of planes, then you're able to propagate that to all the other shapes, right? So here you see that with that, you're able to perform a co-segmentation or consistent segmentation of a set of objects like the airplanes. Now, a bit of a mini summary of what I've talked about so far. So we've seen several examples of simplicity or compactness used as priors when we design rules. For example, when we came up with the symmetry hierarchies, we had these 7 handcrafted rules. So simplicity was one of the guiding principles. We could also use them as priors or inductive biases for network design, right? In a very simple way, right? For the graph network, we simply force the length of the latent code to be limited to have this bottleneck layer. And for BAE and BSP net, we limit the network capacity, right? So for BAE, that results in simpler parts, and for BSP, that resulted in compact meshes, respectively. But what has sort of eluded me actually over quite a while is, well, compactness, could that be defined into something which is a form that you can actually optimize? Could that be a differentiable loss that can actually model the compactness? So this would be very different from using compactness simply as a prior, right? Essentially, it's fixed. It's kind of handcrafted into the network design. So I actually have no idea how this could be done. That'll be actually quite interesting, right? So you force compactness, but you don't force the same kind of network length or network capacity to the entire method. Symmetry. We saw symmetry. Identification of symmetry leads to redundancy, and that leads to efficient or compact representation. There are also other examples where symmetry priors can be used to facilitate shape understanding. This was very old work we did in 2009 on 3D shape segmentation. So if you look at this shape, the one on the top left here, and if you perform a traditional segmentation, a very typical one is to find cut boundaries near concave areas. And if you say 5 parts, why 5? Because from my understanding of the shape, it's four children standing on a plate. So that would be my interpretation. So that's why I want to find segmentation with 5 parts, 4 children and a plate. But just using this criteria of finding cut boundaries near concave regions, it wouldn't give me that segmentation. Now, this is the perfect segmentation. How would I obtain that? The simple idea was to realize that most objects are self-symmetric, right? So if I were able to identify the major self-symmetries, these are intrinsic self-symmetries, then I would be able to find a segmentation of the shape into 4 children standing on a plate. So this one uses a non-local criteria, the fact that objects are mostly self-symmetric. So with this simple idea, the segmentation problem essentially became the problem of detecting major intrinsic symmetries. As you can see here, we're using a way to detect the intrinsic reflection symmetry axes in a shape, and that resulted in the segmentation that you saw for children standing on a plate. There are other examples. A more recent one, this turned out to be the best paper award from last year's CVPR, using bilateral symmetry prior for single view reconstruction of 3D objects from images in the wild, like faces, right? Faces of a cat, faces of a human. Now, symmetry is tied to functionality, right? So I'm kind of turning the page to the second part of my talk. We saw symmetry grouping is one of the Gestalt laws, right? But there's another connection that I want to review. That symmetry grouping is almost like functional grouping, right? Because it's pretty obvious that the symmetric parts tend to perform the same function. I cannot find easily an example where symmetric parts do not perform the same function. So that was something actually we realized even back 10 years ago, right? So I think we wrote that, functional organizations are tied to symmetry grouping. However, symmetry grouping doesn't really tell what the function is. It only tells you that these 2 parts, which are symmetric, perform the same function. But to know what the functions are, we need to see a usage scenario, right? So here we see a person sitting on a chair. We see the functionality of the seat, and we also see that the person is resting his arms on the 2 armrests, and we see the functionality of the armrests. So the key here is to have a notion of this usage scenario, to be able to model that and possibly to learn it, and eventually possibly to be able to generate it. The usage scenarios require agents that perform the action, the function, and also interactions. So essentially interactions between a 3D object with other objects. These objects could be humans, and could be hands, and could be other objects. In a scene context, reflect the functionality, right? So this person is riding a bike, and then this coat rack is kind of quote unquote interacting with these clothes here that are on the rack, and this person is pushing the cart, and this cart holds another human or whatever object there is. So again, the agents can be humans, or hands, or it could be other objects. So very early work, they were referring to the notion of affordance. So affordance is what the environment offers or affords in the individual. So here the individual really mainly referred to humans, possibly human hands. And there's the classical book by Gibson talking about affordance. Affordance has been utilized in computer vision, I believe, for a longer period of time. when I think of affordance analysis computer vision, I always go back to this very classical paper from CVPR 2011. It was called "What Makes a Chair Chair?" Okay, so there the idea is to try to categorize object in a scene, but instead of using appearance attributes, right? They try to fit a canonical human pose, like a sitting pose. Okay, so you have a canonical sitting pose, and then you try to fit that pose into maybe your scanned 3D scene, and then you're able to identify places where a person can sit, right? So then that way you can actually identify not just the chairs, but also sofas, maybe other sittable surfaces in the scene. And the paper was really a pleasure to read. And the paper also started with 4 quotes. I've written papers that started with a quote, but I've never put in this many quotes. These quotes are really informative. So I'll pick 2 of them. So one quote from Nelson that says, an object is first identified as having important functional relations, and perceptual analysis is derived of the functional concept. Another quote, again, to highlight the importance of functional understanding. There's little we can find in common to all chairs, except for their intended use. So these are all motivating factors to using affordance or functionality for inference first perception. In computer graphics, I refer to this paper from Volva, perhaps always already here, from CGraph 2014, and the paper was called Shape to Pose. You can think of this maybe as kind of the inverse of the previous paper. You take a 3D shape and you try to predict human poses based on affordance, right? So this way you're able to infer how human would interact with the given shape. You see examples here on the slide. And fast track to 2020, this is recent work from Google DeepMind to show the relevance of affordance analysis in reinforcement learning. So essentially, with affordance constraints, you're able to restrict the search space for your agents to enable faster learning. So I've always thought about the importance of functionality, right? So actually, when we did the symmetry hierarchy, functionality became relevant. So I believe, again, with all the motivations you've seen, I hope you agree with me that the ultimate goal of 3D shape understanding is actually at the functional level, right? So we humans live in a 3D world, right? So we don't just see and observe, right? We interact, we use the objects, we interact with the environment, we act on them. Right? Now, our understanding certainly doesn't stop at labeling, classification, or categorization. We don't just post these post-it notes on the objects and that's it. We actually need to understand how things are and how to use them, how to interact with them. So this is from the understanding perspective. I'd also argue that from the generative perspective, the goal is also functionality, right? You ask yourself, why would you want to generate something in 3D, whether it's a 3D object or it's a 3D environment? So I believe the purpose is to use it, to use the 3D objects, and for the environment is to interact with it, right? So the generated 3D shape or environment must serve its intended purpose. Comparing shapes versus comparing functionality. So if I give you 3D shapes here as shown, so ask you which 2 shapes are more similar. If you take a typical shape descriptor, you may think that these 2 shapes are similar from their appearance or from their structure or from their shape. But now, in terms of functionality, you really have to review the functionalities by showing how these objects are being used to show a context. And then you realize that the last 2 are functionally more similar. In fact, they perform the same function. Now, in our pursuit, so there are a lot of works here have been done in collaboration with Alex Shamir and other collaborators. The first pursuit was to try to come up with a descriptor of object functionality, right? And this descriptor is going to be based on interactions between objects and objects, right? So here we see that there's an orange object. So this is the object for which we want to describe its functionality, and it's put in the scene context. We have to have the scene context to be able to describe its functionality. And then we're going to describe a descriptor, and then the similarity between the functionalities of the objects is going to be based on some distance measure between the descriptor. Right. So again, so that's the table. This is the orange object, and we define a descriptor. This is handcrafted. Right? We call it icon or interaction context. So it's a hierarchy. So at the leaf, we have these individual objects like a plate here. And then this node here is going to encode the interaction between the plate and the object in question, which is the orange table here. Similarly, you have a chair object, and at the leaf node here, you describe the interaction between the chair and the table. Now, for an internal node, the internal node actually groups objects that have the same functional interaction with the table here. As you can see, all these purple objects actually have the same interaction. On the other hand, the chairs have the same interaction with the table. That's why they're being grouped into this internal node, right? Okay, and then for different objects, we have different icon descriptors, each of which is a hierarchical representation or grouping of the interactions between the objects in the scene and the object in question. And we can compare. Here we realize that there's a lot of similarity between the two icon descriptors. So a bit more detail, how do we model this object interaction? So here is a plate, and here is a table. And we first model interaction by using a descriptor which is called IBS. This is from previous work by Zhao et al. And the IBS is a trimmed Voronoi boundary between the objects. So Voronoi boundary is a set of points which are equidistant to the table and to the set of plates here. And we trim it, and then we encode geometric and topological information of that trimmed surface patch. So that's IBS. And in addition, we also care about the object geometry near the region of interaction, right? So we have some descriptions of which is called IR, which is interaction region, to model the object geometry. And we combine IBS and IR into the icon descriptor to model the interaction between an object with another one. But interesting question here would be to how to come up with this hierarchy, right? This problem really bears some similarity to the construction of symmetry hierarchy. In fact, our development of these functional descriptions also kind of follow this path of first having a handcrafted descriptor, and then eventually we'll get into data-driven and learning. To order the interactions to come up with the icon hierarchy, back in 2015, we just used some handcrafting heuristic merging rules that was model-driven. And another thing that we wanted to extend was the fact that the icon descriptor is on a single object. It doesn't really reveal an understanding of a category, which triggered our follow-up work. The question is, what makes a chair functionally? If you look at the set of chairs here, there's a lot of variety in terms of their structure, variation, and the geometric variation, but they all are chairs. So how do we come up with a functionality model, okay, that describes the functionality of all of these chairs? So that project, so let's call it icon 2, is to learn a functionality model of an object category, like this push carts or chairs. So we started with these icon descriptors, right? And which were again formed by merging heuristics. And then we'll perform analysis of this set of icons for a shape collection. And this is called co-analysis of these interactions. And then we're going to find a correspondence between these functionality descriptors. And these correspondences will tell you different types of interactions. So here you see that there's interaction between the floor and the objects, interaction between the objects that are being contained, these green ones, with the push cart, and also interaction between the human and the push cart here, where most of the interaction would happen at similar locations, which are the handles. Okay, so this correspondence analysis would allow us to identify common regions on the objects, these push carts that perform the same functions. And we call these functional patches. Right? These functional patches reveal where the interactions happen for a particular functionality. So here you see that the functional patch, which is a probabilistic map, tells you that the interaction between the push cart and the floor are most likely happening at the bottom of the wheel. And then here's another interaction, which is interaction at the handle. And again, this is a probabilistic map to review the likelihood of a point that is involved in such an interaction or function. And finally, we have a probabilistic map for the containment functionality of these push carts. And we put these patches correspondence. You see different interaction, and these patches collectively are called a prototypical patch or proto-patch. And the functionality model would encode unary properties of these patches, right? They share certain common geometric properties. And then we also model spatial arrangement relations between these proto-patches. So these would be the binary properties. The combination of the unary properties of the proto-patches and the binary properties would give us the functionality model. And now, given the functionality model, which is constructed from a shape collection, and then you give me a new query shape and able to perform evaluation to obtain a functionality score to tell you how likely that the query shape belongs to the same functional category. Okay, so that's a quick overview of the follow-up called icon2. So it learns a functionality model for a category of 3D objects, such as what makes a chair functionally, and also with other objects. Yet there were still some unanswered questions or limitations of icon2. So first of all, the functionality model learned was still of a whole 3D object. So it didn't take into account of the dynamics of an object. For example, the parts can move, right? In fact, the movement or motion of the parts can reveal the functionality, right? So everything that we have done so far was static functionality, no motion or mobility. And another was this dissatisfaction that the icon descriptor, this hierarchy, again, was constructed using handcrafted merging, and it was the base for both icon 1 and icon 2. And we were hoping to change that, to actually learn interactions using a data-driven approach. So that led to 2 follow-ups. The first one is to learn how object parts move, right, to predict, which we called part mobility, to allow the modeling of dynamic functionalities, like the turning of the top of the faucet, the handle here, and then a motion of the syringe here, right? The key here is that we should be able to predict the part motion or part mobility by only looking at an input that is a static snapshot. Okay, so one particular snapshot of the state of the object, and we're able to infer its motion. So if you think of an application in robotics, right? If the robot comes into a room and wants to interact with this cabinet, and by just looking at from a static perspective, it is able to know how to interact with it. This is the way to open the cabinet door, and this is the way to open the drawers. And this was learned from a data set of part motions, right? And one limitation for that particular work was that we needed the 3D objects to all have perfect segmentations to learn the part mobility. And with that, we followed with a work from 2019, which is called RPMNet. So the key innovation there was to remove the requirement that the input object had segmentation. So we're able to work with scans, okay, just a rough scan of a 3D object, and then we're able to infer its part mobility. Okay, the key idea is actually to decouple the motion prediction. First, we do not know what the motion type is. We don't know whether it's a rotation or whether it's a translation. We just try to use a RNN, or recurrent neural network here, to predict the sequence of point displacement, right? So I wouldn't go into the details here. If you're interested, you can check details in the paper. And after we've learned this sequence of point-wise displacements, and then in the second step, we are going to use motion estimation to estimate the parameters of the motion, and then to be able to learn what kind of motion it is, and the axes and other things. So as I said, this will be very important for a robot to be able to go into an environment, to be able to understand how to interact, because the robot could have an RGBD scan of the scene, and it's able to use something such as the RPMNet to be able to infer the motions of the objects. And I can also envision that in AR applications, instead of having the environment being passive, that you may have some kind of avatar jumping around in your environment, that with an understanding of the part mobilities or functionalities, then you may be able to interact with the object in an AR environment so that the objects actually can perform the expected motion. And then finally, I want to talk a bit about this work called Icon 4, which takes an input 3D shape, which is an isolated 3D shape, and eventually be able to hallucinate or predict its functionality by showing how a human or other objects may interact with this given object. And along the way, we finally had a functionality description that was learned without being a handcraft like the icon work that we did back in 2015, right? So again, the input here is an object in isolation, okay? And first we turn that into a voxel representation. So this is voxelization of the input, that's all. And then we have a network, which is called FSymNet, that is able to retrieve from a set of scenes that show all kinds of interactions between objects and its surroundings, and is able to retrieve a scene with a label, right? Please do note that in the retrieve the scene, this object here is different from the input object, but it performs the same function. And with this retrieve the scene and label functionality label, we're able to, so let me just show you here, we're able to use another network, a generative network that is able to generate an interaction with the very input object, which is shown over here. And then you can perform segmentation, and then you can retrieve actual objects to review the functional interaction with input object. So the sort of the key technical problem that we needed to solve was actually the very first network, the FSymNet, which would allow us to take an isolated 3D object and to retrieve the right interaction scene. So that network turned out to be a cross-domain triplet network. The reason I call it cross-domain is because this network, this triplet network, is able to map both objects, isolated object, which is this one here, and scenes. Okay, these are two interaction scenes with objects and their surroundings to the same latent space. So why this is a cross-domain triplet network. And the input of this network would be one isolated object and another object with its scene context that review the same function, which is the Y here, and another scene context that where the object performs a different function, as is typical in a triplet network setting. So the network learns functional similarity between the objects and the interaction scenes. So this two networks that maps the scenes to the latent space, they share weights, but this network here is different. Okay. Instead of mapping this input object into a single scene context, it maps to a distribution of scene context. That's because this particular object could perform multiple functions, right? It's to allow the input isolated object to map to different kind of interaction. So that's a mapping to a distribution of the scene context in the same latent space. Okay, so I will give you a bit more details. I'm not sure how I'm doing with time. I hope there's time to play this video, and then I'll conclude. I think usually Zoom has a bit of a voice transmission problem, so that's why I'm going to share this on my Chrome tab and then play the video. Just give me 1 sec. I'm trying to find my. Sorry, it looks like the voice didn't work. Let me just give me 1 sec. I apologize.
Richard, I think the video is also not playing, so.
Oh, no. Okay, so maybe I can try to see if I can play from within the. Sorry about that, guys. Let me stop sharing. See if I can share. Yeah, this is always a bit risky. Let me share again. I do have the videos embedded, but I often have trouble with at least the video will, I think, will play here. The voice, I'm not so sure. Would you be able to tell me whether the voice
We can't hear anything.
Okay, so I guess I'll probably, because I'm going a bit over time, so I will probably just forgo the video play, and certainly everything is available. If anyone wants a link or anything, please feel free to ask me. So let me actually just conclude, and then we can go into the panel discussion. So I talked about evolution in my talk title. So as you can see from this the sequence of the slides, you see that there's an evolution from symmetry analysis to functionality analysis, realizing that there's a connection between them very early on. There's also an evolution from low-level representations, maybe point-wise descriptors, to segmentations, and eventually to hierarchical representations at the structural level. There's certainly an evolution from the older works which were model or rule-driven to data-driven and learning-based approaches, eventually using deep neural networks. In terms of functionality, one of the main challenges is data, right? It is much more difficult to collect these interaction context data, like between objects and its surroundings, maybe humans or hands. It's much more difficult to collect, describe, and certainly to generate such data. And already we talk about 3D being not as ubiquitous as we hoped because of a lack of 3D data. If you look for 3D data that have functionality annotations, it's considerably less compared to other kinds of 3D data, just like things from ShapeNet. And finally, I ask the same question: is it possible to have functionality as some kind of function network loss to be able to optimize functionality in the deep neural network setting? So that also seems to be an elusive question for me. So finally, I'd say that I started with talking about symmetry and compactness as a way to come up with good shape representations to facilitate understanding and generation, but functional understanding and generative modeling is the ultimate goal, because I truly believe that the reason we generate in 3D is for them to serve their intended functions. Okay, so that's it. These are the papers that I've covered, and I certainly like to thank the students who did most of the work, and also my collaborators on this set of papers that I just covered. Thank you very much.
Okay, thanks, Richard, for the very inspiring and wonderful talk. So we'll ask a few questions from YouTube, then we go to the panel discussion. So the first question is, so do you see the application of those methods in industry like furniture design, like function-driven furniture design?
Oh, I certainly do. In fact, we've had some discussions which I may not be able to really review. In fact, if you think of IKEA furnitures, and in fact they're structural, right? So you don't want to model them or design in terms of at a voxel or point level, right? You think of them as a structural level design. In fact, not just us, other people, I can name a number of groups worked on furniture designs at the part level. So does that answer the question, I hope? So there's a lot of potential there.
Yeah, thanks. Okay, so the second question is, so how do these methods work on like architectural models and tree models? Do you see applications of to those models?
So I have to think specifically which I've covered many works. So from the representation level, I think the let's say, symmetry hierarchy, the particular representation would certainly apply to architectures. And the generative models for, we actually had a just CVPR paper recently called the roof GAN. So certainly these kind of architectural models from, designing of roofs certainly would be relevant. Trees would be a bit different. So I'm not sure whether things like symmetry hierarchy or INet are primed for representation of tree models. They are more complex, less structured. In terms of modeling trees and these sort of more organic objects, there are certainly a lot of works already, especially on procedural modeling. There are also works on inverse procedural modeling of trees. I haven't done a lot of works along those lines. So one thing that may be relevant is, again, we have a recent work, which is called the decor GAN, which is able to take a very coarse voxel grid and to be able to detailize it by adding details. So we had an example showing that it can get pretty good results for plants. I think trees would be also workable if you have the data. So that's work I think Volvo was also involved in. Yeah, so architecture, I think for sure, trees less so, but there are already other approaches for tree model.
Okay, thank you, Volvo. Now we open the questions to the panel panelists. Maybe we go with Eric first.
So, would you like me to ask questions or to answer questions? That's the.
We can do all of it.
Yeah, we can do both. So I would say one thing that I think for me is a challenge is that you started by constructing and thinking about objects and their structure in a certain way, and we agree that the structure of parts and the hierarchy and the meaning of those parts, specifically as you mentioned, the functionality and the symmetry of those are very important in order to, or are very important in terms of the representation itself. Now we have this amazing tool that in vision works so well, which is called neural networks. And many times when we try to apply neural networks on three-dimensional shapes, we have to convert them, as you've shown, to voxels and things that are very low level in a sense. So I think this gap is something that bothers me very much. And I'm trying to think about whether you think there are other ways. Of course, you showed some, the recursive networks and other ways to tackle this huge gap between the abilities of neural networks to understand, let's say, images, because they are very structured and they have this grid-like structure, and three-dimensional objects. So do you have any ideas on this, or any directions on where we should go in terms of really giving neural networks the correct representation that we think three-dimensional objects should be represented, and work with this and not work with the low-dimensional voxels or similar, representations? Yeah,
exactly as you said, with this use of this the grass and the grains later for the scenes. So I do believe that you don't really have to go to the very low level of representation to understand. This RBN for essentially box abstractions, and I think that's probably a good way to go for understanding and also to generate shapes, right? So most of the generative neural networks go for voxels and points and non-neural implicits. But with grass, you're able to generate first the structure, and you fill in the geometry, right? This kind of coarse to fine generative model has been applied by other groups as well, right? In fact, I'm also going to expand a little bit on. So recently, I've been thinking about this, very typical problem, which is like a prototypical problem in computer vision, which is single view reconstruction. Years ago, I had a paper which was called a photo-inspired 3D modeling, where essentially we just do retrieval, right? We take a single photograph of a chair, we retrieve from a set of 3D models, and we do some deformation. So it's perfect that then Qixing had a work, which year was it 2015, right? And did it much better. And then we look at all of these single view reconstruction works, like the AtlasNet, the INet, and the DSN and everything. And look at the results when they apply to images in the wild. They are pretty bad, I would say, right? And I go back and think, is it really the right way to take an image and encode it using ResNet and just basically forget about what the shape is, just go from that code and then try to reconstruct it in 3D? In fact, was a paper which says that most of these single reconstruct networks actually do not beat retrieval and classification. I think that's one from Intel. So I say, why don't we just go back to the old ways, right? Why don't we actually admit, let's just retrieve, right? Let's retrieve and deform, right? And the retrieval here would be from a collection of highly structured models, like the symmetry hierarchies, right? So one must be smiling because you guys just had a paper called Joint Learning of Retrieval and Deformation, something was serious. So I think I actually truly feel that's the right way to go. And we just need to do a bit more with the deformation to allow topology changes, to do more of a faithful reconstruction instead of just retrieve and then do a bit of modifications. So in that way, I think although the neural networks are designed, perhaps the traditional ones anyways, are designed to do this low-level processing and saying that everything has to be learned from scratch from the very low-level representation, but it doesn't have to be. I think maybe the best results are going to be obtained by realizing that there is a bit of a gap between the high-level structural representation and the low-level geometry. We can do that separately.
Okay, thanks, Eric, for raising this question, and thanks, Richard, for the comment. I would like to hear from Vova about this kind of representation, right? So, issue for 3D learning in particular, if you think about like what we have developed during the past like 5 or 6 years compared to what we have, right? So in geometry processing graphics for the past 5 decades or 4 decades, something like this.
Yeah, so I mean, I guess just to confirm, is your question about where we are and where we're going in terms of representations? Is that what you're asking? Yeah. Yeah, I mean, I think kind of we have a lot of tools that show that if we handcraft decomposition of the shape, right? Like we can, as Richard said, we can like represent our shape as an arrangement of bounding boxes and then have some kind of either retrieval-based method or deformation plus retrieval or reconstruction-based, through voxels, through implicits, kind of model geometry of these boxes, and have something else on top of this, like decorgan that we did with Richard to kind of model the decorative elements that could have even more diversity. Then I think we can get a pretty compelling output once we stitch all these elements together. And I think that's where we are. One of the next steps for me is how do we have this decomposition to arise naturally from the data, as opposed to us kind of annotating and decomposing manually and picking and choosing what is a part and what is the kind of geometry of the part and what is the decorative detail on the surface of that part. So I think it's I envision that in the future we don't want to train on these highly annotated data sets. Probably we don't even want to train on geometries. We want to probably train on images and just have some network that builds this internal representation for objects from very sparse, unorganized type of training data. And the ideal output of this is that it's one representation that just has flexibility to shift information here and there and then represent it in different ways. So it could naturally understand that objects are arrangements of kind of repeating elements, and then it needs to represent geometry of these elements. And then maybe there are kind of unique decorative details that you might not even be able to build a full generative model of these details, and you just need to optimize it on the fly for specific task. And the task could be, say, image-based reconstruction. Then you can have some additional guidance on what needs to be added to your model and what kind of priors you can utilize when you can't learn the full generative priors. You can't expect that you'll generate the object exactly as it appears in the image, just because it's impossible to observe every single object during training. So that's one direction. I do want to just kind of comment and maybe ask additional questions. So I like this other direction that Richard described in terms of kind of functionality of objects, right? And I think this is something that we're still missing, is that we have these digital models, but objects are physical objects in real world. So they have reflective properties, they have physical properties, they have particular functional properties of how people use them, and we are on that front, we are very, very early stages. We still need to do a lot of research to actually build appropriate models. I think I just want to add that I feel like one big piece that's missing is also, apart from data, is also a good biomechanical model of a person. So if we have this and combine it with this icon-like representations for the functionality of objects, that might lead itself to many, many interesting applications in object design and maybe room design and layout design and so on and so forth.
Yeah, I have a few things in that I want to say. So first of all, so I really wish that more people will be working on functionality. I think maybe one of the reasons why not so many are working on it is because of lack of data. So that should be fixed. We have Sapien, right? I think now there's the more new data has got a behavior. So these are all, if you check out some of the work from David Fohe and also Stanford Fei-Fei Li. So there's a lot of efforts, right? So that may be one reason why there are not enough people working on functionality yet. Aside from what I mentioned, there's another thing that's missing, which is to have generative models of texture. I think that's still very much lacking. Right? Most is just like, just geometry, like, gray shaded geometry. But we try to do that a bit, but we're not able to really do it right without actually functionality, because the actual texture really depends on the material, and the material actually depends on the functionality. So without a functional understanding of these objects, we are not really able to get the texture synthesis or texture generation right. So I think that's certainly one more reason why I think working on functionality and collecting data on functionality is important. In terms of getting away from these, structured annotations, I want to go back to this notion of compactness or simplicity or MDL, right? There's a lot that we don't know how to do, right? For example, I worked on inverse CSG, try to come up with this construct solid geometry trees. But I cannot somehow put together a reconstruction loss and this loss that essentially tells the network to give me the smallest tree, right? I don't know, I probably need to learn more from what other people in machine learning have done. Is it possible to actually combine these two losses together to come up with the smallest tree, right? Everything that I have done so far is just to say that here is let's make the code short. Let's make the network small, right? We essentially handcraft the network capacity or the code length. There's no flexibility. There's no minimization of the tree size, right? For CSG or symmetry hierarchy. So there's something fundamental there. Maybe someone already knew how to do that. I'd be very happy to hear what can be done there. I truly think that if we all believe all comes razor, then coming up with the minimum description length model actually give us a lot more than we would expect. But it's just right now we're very primitive in terms of how to inject that into our network design. We start to handcraft some hard constraint in the network design.
I would like to throw in one more notion, which I think is important, especially in terms of the Occam razor and minimum description link, and it's called abstraction. And in a sense, I think that once you have an object in front of you and you can abstract it to its minimal function or minimal shape, then what you get is exactly what you want. It's the minimal representation of that object as a functional object. So maybe not just working on functionality, but also working on abstractions of objects and abstractions of maybe images or videos. That's another pathway to go through and understand these types of general representations.
That's absolutely true. So I'm that sort of that's another recent thought that I had. So I mean, we worked on like geometry templates, right? So a lot of work for like a template fitting of some sort. We have this geometry templates, but I really think that we should start thinking about functionality templates. I believe the number of functional templates is actually much less than the number of like shape templates or geometry templates or structural templates. So I think I cannot easily list 260 functional templates, right? I don't know, maybe I don't know how many categories there are in ShapeNet. It's definitely more than 13. It's something 260, right? But if you think of functional templates, maybe this is the kind of abstraction you're thinking about. Maybe when we humans look at something, we try to abstract in a functional way, what it does, right? Not what it looks like, right? So maybe there should be a collection of functional templates, and that shouldn't be too big, and that actually can help us have a unified understanding of a lot of things just by looking at them from a functional perspective. So that data set may not be as hard to do. I mean, maybe it's kind of handcrafting functional templates, and then do something with it. Just a thought.
Okay, thanks, Richard. Thanks, Eric. So I would like to, since Richard mentioned the data issue, right? So for learning and functionality, I would like to ask this question, right? We have a lot of videos, right? So demonstrating how humans interact with objects, right? So that can certainly reveal some functionality, right? So my question here is that, do you see this kind of joint learning from images or videos with shapes can potentially address this issue, and what is your thought about this?
Yeah, so that's a very good point. I mentioned David Fohe, and he, I think even a few years ago, he had I'm not sure if David had given a talk here or not. He had a vlog data set, right? And the behavior, I just saw that on Twitter from Fei Li's group, is actually on, again, everyday activities of human doing things like, polishing shoes and opening a microwave and putting things in there. So this video data, like a vlog, is easy to obtain. There's a lifting problem, right? So joint learning, I think there's still a big gap going from this video data to something three-dimensional, right? So again, maybe that's the whole challenge. It's like a chicken and egg problem, right? So the general belief is that to be able to augment the 3D data, you need 3D data, right, to train, right? But it's so much easier to obtain the video data. I'm not sure how easy it is to do a joint 2D, 3D learning when there's a severe imbalance between the 2D and 3D data, right? So maybe that's a challenge to address, right? When you have...
That's Richard. So Eric, you worked on both images and 3D shapes. Do you see this kind of, there's a potential of transferring this kind of functionality from images to 3D models as a potential, something that will happen in the future?
I think that's one of the main challenges that are still out there, because as Richard was saying, thinking about functionality in terms of abstraction, which is more verbal. So, in vision, you recognize action in many works, and these actions are represented by verbal things, action labels and things like that. But when you convert them to three-dimensional objects, then first of all, as Richard was saying, there's much less data, and converting any two-dimensional data like images and video to three-dimensional is a challenge by itself. And so I think there's a huge gap there. And one of the things that people often think about is they say, humans are, they learn by looking at things, right? So babies look at things and so on, but they tend to forget that babies also interact physically with the world. And this is something that closes the gap much more than just observing things, right? And this physical thing is something that's missing, I believe, in all of vision, in a sense. So when you think about three-dimensional objects, how to interact with them, how to open them up, how to use them, is something which is much more coming from the three-dimensional world than the physical world. And I actually think that the gap won't be able to close just by looking at videos and images. And there's a clear distinction there that, I'm not sure how to close this gap, but there is a gap there that I actually don't think that only videos would be able to solve. So maybe I'm a bit pessimistic in this sense, but I see this gap, prevailing still.
Yeah, so there are a lot of emerging works on this in robotics, right? They're trying to install interactions with 3D understanding, right, into the loop using maybe there's a potential over there. So Voa, thanks Eric.
Exactly.
Voa, what is your thoughts on this issue of what Richard mentioned, this kind of training data issue, and how we should address that? Big picture.
Yeah, I mean, I think I agree with Eric that there is definitely a gap between how people learn and how machines can learn because of obvious limitations. Also, humans are actually very much hardwired, right? Like I don't know, in my kids, I see that their brain just develops in a particular direction. There are some connections that are just forming at every year, and I don't think a lot of it is coming from the environment. I don't think they need to interact or observe anything. It just biologically kind of predetermined through millions of years of evolution, and it's not like they're training from scratch, right? Like there is already a neural network that kind of naturally connects, and then it's been pre-trained and it's been training for a very, very long time on a very, very efficient simulation. So that's something that I think is going to be difficult to beat. I think just ability to train from data that's available and build representations that are agnostic to the type of training data you feed into it, right? Be it images, text, videos, and all these modalities that are available at enormous scale online. I think that's something that's not very common in 3D yet, but I do feel like that a lot of work is kind of coming in this direction where people want to rely less on the availability of 3D data that's still quite sparse and more on the data that's available at scale and for free. So being able to handle multiple modalities and kind of integrate information in a meaningful manner from these modalities will give us some results. I don't think we are any close to beating the hardwired human brain because it's it's difficult.
Okay, so we are running a bit out of time, over time. So Richard, do you have any final remarks to make?
I hope more people will be working on functionality. I
knew you were going to say that.
Yeah,
I knew that this is your final word.
I mean, we haven't
functionality.
I mean, Eric and you and I, we haven't even really followed up on that. I mean, that's hard to blame SunCG, I guess.
No, I blame the COVID-19 for that.
That too as well. Yeah. I mean, I think this notion of functionality template, maybe there's some merit to that, and the fact that maybe there's less functionality. I mean, one functionality template may cover many shapes, just like one sitting pose can handle sitting on chairs, sofas, benches, tabletops, and everything, right? So that may be a more compact space to work from than going from like the shape space. So maybe that's maybe a parting thought.
Okay, thanks again, Vishu, for the talk, and thanks Volva and Ivy for the panel discussion. So this concludes this week's 3D TV seminar, and see you next week.